In this question, we're going to graph the curve y equals 1 over x squared minus 6x plus 12. Well, first we find where our y-intercept is by letting x equals 0, and we see that y is 1/12. So we have a y-intercept at 0, 1/12. We have an x-intercept where y equals 0, but that would mean that the numerator of 1 was equal to 0, which is impossible. So there's no x-intercept. Now, we see that y is never undefined because x squared minus 6x plus 12 never equals 0. That should say y there. Because the denominator never equals 0, the value for y is never undefined, so we're not going to have any vertical asymptotes or holes. To check if that's true, we can let x squared minus 6x plus 12 equal 0. We see we would get a negative discriminant, so it's not possible. So there are no vertical asymptotes or holes. There is, however, a horizontal asymptote at y equals 0 because the curve is degree 0 over degree 2. Okay, now y is equal to 1 over x squared minus 6x plus 12. In other words, it's equal to that quadratic expression raised to the exponent of -1. That means y prime is -1 times the quadratic expression to the -2 times 2x minus 6. So we can simplify to this. Now y prime is never undefined because, as we said a minute ago, x squared minus 6x plus 12 never equals 0, and in fact is always positive. But y prime can equal 0 where the numerator equals 0. Well, that numerator equals 0 when x equals 3. So there's a critical number for us, x equals 3. Now, since the first derivative is equal to this expression, which can be re-expressed as this, the second derivative is equal to the denominator times derivative of the numerator minus the numerator times derivative of the denominator. Now, when we do that, we see that we can common factor x squared minus 6x plus 12 from this first part and from this second part. So in the second step, that's what we do. We factor out x squared minus 6x plus 12, and we're left with this expression as the second factor. Well, we're able to cross out this factor with one of these 4 factors, which gets rid of it in the numerator and reduces the exponent in the denominator to 3. And then we use the distributive property to figure out what our numerator is, and we collect like terms. Then we see we can do a little bit of factoring. We common factor out the 6, and then we see we can factor this trinomial to x minus 2 times x minus 4. So that means that y prime prime is never undefined, but y prime prime can equal 0 when x equals 2 or x equals 4. The numerator equals 0 when x equals 2 or x equals 4, but the denominator, as we've said earlier, never equals 0. Okay? So we've got an expression for our first derivative and an expression for our second derivative. So we stack our interval testing, and we see that when x is a number less than 3, we have a negative times a negative over something that's positive. That's positive. But when x is greater than 3, we have a negative times a positive over something that's positive, and that's negative. So we're increasing to x equals 3 and decreasing after. Since the function is defined at x equals 3, we're going to have a maximum point there. Our second derivative has intervals at 2 and 4. To the left of 2, this whole expression is positive. In between 2 and 4, this whole expression is negative. And to the right of 4, this whole expression is positive. Now, we see that we have a maximum at x equals 3 because, as we just said, at x equals 3, the slope is 0, and we're increasing and then decreasing. But another way of establishing that is to say that at x equals 3, we have a slope of 0, and the second derivative is negative, meaning we have a maximum there. Well, at x equals 3, y is equal to 1 over 3, so we have a maximum point at 3 1/3. And at x equals 2, y is equal to 1/4, and at x equals 4, y is equal to 1/4. These are the numbers at which the second derivative equals 0. So that means we have points of inflection at 2, 1/4 and 4, 1/4. So to summarize, we have no x-intercepts. We have a y-intercept here. We have no vertical asymptotes. Please note that says vertical asymptotes or holes. But we do have a horizontal asymptote at y equals 0. We have a maximum point here, and we have points of inflection at these 2 points. And this is our interval testing table. So what we're going to do is we're going to plot these 4 points on a graph. Now what I've done here is I've cheated a little bit where I've made the y-axis be 12 squares per 1 unit, and I've made the x-axis be only 6 squares per 1 unit. I just wanted to fit it on the page. So what we see is that to the left, let's start with to the right of 3. To the right of 3 we're decreasing, and at first we're concave down. We're decreasing and concave down right up until this point. Now at that point we become decreasing but concave up. And we treat the x-axis as a horizontal asymptote. Ideally, it's a little hard to do with a thick magic marker, but ideally this is the point at which the tangent line goes from being above the curve to below the curve. So I probably did a decent job there. Now on the other side, we see that we're increasing the whole time, and we can kind of tell that. We're going to be concave down in between 2 and 3. So we're concave down, meaning the curve will be below the tangent line. But then from this point on, we're going to be increasing, but we're going to be concave up. So ideally, this will look like we are going from having a tangent line below the curve to above the curve. And if we've done that decently, then we've done a decent job of graphing y equals 1 over x squared minus 6x plus 12.